When prompting an AI to build a simple utility app, like a calculator or a to-do list, basic prompt engineering is sufficient. But building a multi-user ecosystem with distinct roles and cross-regional data requires a shift from feature requests to structural directives. A prompt that merely lists features often leads to a collapse of database relationships. Tables become orphaned, permissions bleed across user domains, and the underlying logic becomes a knot of contradictions. We are using the Cohandy operating system as a stress test for this problem. This is a platform designed to coordinate physical stewardship missions between youth, parent stewards, and professional mentors. The requirements are complex. The system must enforce strict safety protocols for minors, mandatory oversight gates, and logic that scales across international borders. Generating a functioning ecosystem of this scale requires moving past simple feature requests. To control the AI's output, we must instead dictate a rigid system architecture. The solution is a master prompt built on architectural principles. It explicitly defines the system through 5 discrete layers. Those layers are identity, capability, action, oversight, and cultural automation. We are translating a text-based master prompt directly into a relational schema, showing how specific instructions dictate the machine's internal logic. In this methodology, the AI builder follows one rule. It constructs only the dependencies provided in the prompt. This creates a direct bridge between the code and the relational structure. The AI interprets this data skeleton to generate its logic. Without a stable schema, the resulting user interface code lacks a consistent structural foundation. We begin with Layer 1, the gatehouse. This is the universal entry point and the primary identity router for the entire platform. The prompt establishes role-based access control, creating distinct nodes for youth, parents, stewards, and regional partners. We attach automation logic to these identities. When onboarding completes, the system assigns the role and routes the user directly to their specific dashboard. Free navigation is disabled. By locking users into their operational domains, we prevent them from accessing functions outside their role. To ensure minor safety, we define a household link, which acts as a mandatory relationship between the parent and youth nodes. This link creates a strict permission hierarchy. A youth account cannot trigger a database write, such as marking a task as finished, without a verification code from the linked parent account. By hard-coding identity and automated routing as the foundation, we secure every subsequent data operation in the ecosystem. Layer 2 is the mission engine, the layer that governs every action a user takes within the platform. The Cohandy mission schema is reverse-engineered directly from NASA's operational reporting for the Artemis II mission. We deconstruct the Artemis splashdown into 3 data types: technical execution, the human narrative, and safety risk analysis. We translate technical execution into a database array, mapping operational steps into a mission template table. The risk analysis converts into a linked safety flags table. Finally, the crew condition narrative dictates the structure for user-submitted proof in the evidence table. We then embed a mandatory parent sign-off variable within that table. The record cannot advance in the system until this Boolean is switched. In a practical youth fix-it mission, like repairing a door hinge, the youth follows the steps, takes a photograph of the result, and uploads it. The data flows sequentially. The youth uploads the evidence, the parent verifies the local effort, and the regional steward provides the final professional review. Translating qualitative operational parameters into a strict relational database provides the constraints an AI needs to prevent logic leaks during generation. Layers 3 and 4 manage the capability hub and the oversight console. Skilled workers manage their capability data through a portfolio-driven talent interface, focusing on skills and innovations. Meanwhile, stewards use a queue-driven oversight interface to manage the mission queue and safety flags. Without precise instructions, an AI is likely to build these as siloed, disconnected applications. To prevent siloing, the prompt forces the AI to use a shared mission instance table. Both dashboards are simply different views of the exact same data row. We assign read and write permissions for this shared table differently. Talent users submit evidence to the row. Stewards update the verification status of that same row. The AI processes these constraints to generate separate front ends that feed into the same back-end data structure. The ecosystem remains stable because we prompted the machine to force disparate interfaces to feed into a single, normalized backend. Our most complex challenge is scaling the role-based access control logic across international borders. This is the objective of diaspora pathways, where a sponsor in one region supports or verifies actions in an origin node, like Accra Metro. We add 3 fields: Region ID, Origin Region ID, and Diaspora Tag. Region ID strictly limits dashboard visibility, blocking a user in the Bronx from seeing Ghana's data. However, the Diaspora Tag initiates a trigger, allowing an automation payload to bridge the 2 nodes using the Origin Region ID. When a diaspora sponsor funds a mission, the system updates the evidence logs in the origin region directly. This architecture allows for external support while protecting the administrative autonomy of the origin region. Scaling a global system with AI is achieved by engineering precise relational triggers between localized data nodes rather than duplicating the application for every region. We can now see the fully constructed system and its interconnected layers. The data lifecycle moves from start to finish. A youth completes a mission, a parent approves, a steward verifies, and a diaspora node logs the global impact. This triggers the final architectural requirement, Layer 5, the ceremony engine. We use this layer to automate cultural outputs, like generating legacy logs or welcome scripts, entirely through database state changes. Once the strict status equals completed logic is enforced, the AI builder handles these ceremonial triggers seamlessly. By doing this, we have successfully moved from a flat, text-based master prompt to a functioning, highly stable relational database. Generating high-efficacy applications with AI requires us to think as database architects. If you master the data schema, the AI can master the code.